Okay, a bunch of our problems this week have multiple events in the same problem, and we will have to decide whether we're going to use conservation of momentum or conservation of energy for each event. So, let's take a look at a problem like it. I'll read it, and maybe you guys can pause and read it a couple of times. A 1 kilogram mass is launched using a spring with a spring constant of 50 newtons per meter, which is initially compressed 10 centimeters. The 1 kilogram mass slides across a horizontal frictionless surface until it collides with a second mass of 2 kilograms. The two masses stick together and start sliding up a frictionless hill. How high will the masses get before momentarily coming to rest? When the masses slide back down the frictionless hill and across the frictionless horizontal surface, they again hit the spring. How much will they compress the spring before momentarily coming to rest? All right. Again, maybe pause and read it over a couple times and try to come up with a picture, a diagram, sort of showing what's happening. All right? Okay, maybe you're back, and I will draw my diagram of what I think is happening. So we have a horizontal frictionless surface, and then we have a frictionless hill. We have a spring, which is initially compressed, and a mass connected to the spring. We'll call this guy M1. In our initial picture, M2 is at rest on the horizontal part. Now, what's going to happen, and actually I'm going to see if I can move M2 a little bit closer here. So in black here, I've got my initial situation. In red, I'm going to draw what happens right before the collision. Right before the collision, we've got M1 moving with a velocity I'll call V1. Okay. And then in blue, I will draw what happens after the collision. After the collision, M1 and M2 are stuck together, and they're moving with a velocity I'll call V2. And then in green, I'll draw the next stage of what happens. We get to the top of the hill, and again we have M1 plus M2, and we'll say that V3 is equal to 0. And then I think that's all I can draw in one picture. You could draw a separate picture for each stage. So what I have here is black first, and that goes to red, and that goes to blue, and that goes to green. And then I'll draw as a separate picture the very last stage, because in the very last stage, M1 and M2 have come back to compress this spring, and they've come to rest. All right, so we have multiple events that are going on here. In the first event, we have M1 being launched. So I'm going to label this 1. M1 is launched by the spring. Okay, so this is going to be solved using conservation of energy. And really, for a particle, because we really just have one object involved in this event. M1 is launched by the spring, conservation of energy for a particle. So when using conservation of energy for a particle, the work done by non-conservative forces is equal to the change in mechanical energy, that is kinetic plus potential energy. Another way of writing this for us, since there is no work done by non-conservative forces, is that energy initial is equal to energy final. All right, so the initial energy is just the spring. So we have 1/2 kx squared. And the final energy is just the moving block. So we have 1/2 m1 v1 squared. So from this, we can find v1. So v1 is equal to, the 1/2's cancel, divide both sides by m. So it's equal to the square root of k over m1 x squared. All right, plugging this into my calculator, the square root of k, which was 50, over m1, which was 1 kilogram, times x squared, which was 10 centimeters, but 10 centimeters is 0.1 meters. So I square that, take the square root of the whole thing, and I get v1 is equal to 0.707107 meters per second. Okay, step 2 is the collision between M1 and M2. Now in collisions, we cannot really use conservation of energy because we know some of the kinetic energy gets converted into thermal energy, and we don't have an equation for thermal energy. So even though it is true that energy initial is equal to energy final, so it is true that 1/2 m1 v1 squared is equal to 1/2 m1 plus m2 v2 squared plus the change in thermal energy, because in that collision, some thermal energy is created. That's this term right here. So for example, if this was 10 joules and this was 8 joules, we know that this would have to be 2 joules because energy is conserved, but we don't have an equation for the change in thermal energy. So this would have 2 unknowns in it, and we can't solve that. So we are not going to use energy for collisions. We are going to use momentum. So for this, we're going to use conservation of momentum. Which means that the initial momentum is equal to the final momentum, which means that m1 v1 is going to equal m1 plus m2 times v2. And what I'm looking at here is the difference between the red picture, which is m1 moving, and m2 at rest, and the blue picture, which is m1 plus m2 moving together at velocity v2. In that collision, we should have conservation of momentum, which means that v2 is equal to m1 v1 divided by m1 plus m2, and that is equal to, let's see, m1 is 1 kilogram, and m2 is 2 kilograms. So this is going to be 1 times the velocity we just got divided by 3. So v2 is equal to 0.2357 meters per second. Okay, now these two things are together, moving at a velocity, and they start to slide up the hill. There's no friction, so there's no work done by non-conservative forces. This is a great situation to use conservation of energy. So we're going to say that energy initial is equal to energy final. And the initial energy here is just kinetic energy, 1/2 m1 plus m2 v2 squared. And the final energy is just gravitational potential energy, mgh. So that's going to be m1 plus m2 times g times h. Now the m1 plus m2's cancel, and divide both sides by g, and I get h is equal to the square root of v2 squared over 2g. Okay, so that is the square root of 0.2357 O2 squared divided by 2 times 9.81. So the answer is 0.0532 meters, which is about, which is 5.32 centimeters is how high it'll go up the hill. Okay, is that what the problem asks? How high will the mass get momentarily before momentarily coming to rest? Okay, and then part B, when the masses slide back down the hill and across the horizontal thing and they hit the spring, how much will they compress the spring before momentarily coming to rest? Okay, so this is really step 4 of the problem. We've got the fourth event hitting the spring. Well, actually, sliding down the hill. Sliding across the horizontal surface and hitting the spring. And the thing is, there's no friction sliding down the hill. There's no friction sliding across the horizontal surface, and hitting the spring also conserves energy. So for this whole process, we can do energy initial equals energy final, which means m1 plus m2 times gh is equal to 1/2 k x squared. Multiply both sides by 2, divide both sides by k. X is equal to the square root of 2 m1 plus m2 gh over k. All right, so I'm going to take the value of h that I got from my calculator, that is 0.053213. So we're going to do the square root of 2 times m1 plus m2 is 3 kilograms times 9.81 times the height that I got, 0.0532125, divided by k, which I don't remember. K was 50 newtons per meter. And that is not the right answer. Right here's my mistake. I, for some reason, took the square root of both sides when I wasn't supposed to. So that height is not equal to the square root of v squared over 2g. It's just v squared over 2g. So let's find that velocity. 0.2357 squared divided by 2 times 9.81, and we get an actual height of 0.0 0.02832 meters, which is actually 2.8 millimeters. So it doesn't go very high up the hill at all. Now we can come down here and find out what x is. X is equal to 2, the square root of 2 times the total mass, 3, times g, 9.81, times the height, 0.002832, or 31523, divided by 50. And there we get our actual answer, 0.0577 meters, which is about 5.8 centimeters, which is less than the 10 centimeters that the spring was initially compressed, because some of that spring's energy got converted into thermal energy during the collision. So when we compress the spring again, it's got to compress less than where we started. Okay, that is the end of this problem, and I'm going to have to edit out some of the stuff in the middle where I couldn't find my mistake.